Hi everyone, today's topic is recursion. I told you that functions are one of the most important concepts in programming languages and even in computer science. And recursion is more important than functions, meaning that, recursions are recursive functions. And that's really important, not only in computer science, but also in mathematics. We used to have two lectures for recursion, one for the concept of recursion, the other for implementing recursion. But thanks to these online lectures, and we can have Q&A session, right? So I compacted two lectures into one. So today's lecture, this material is going to be really dense to everyone, I guess. So be warned. And if you don't understand some parts, don't worry. Everyone is going to be like that. So you can listen to that part multiple times. That's the good thing about online lectures. So really quick review about the language that we've learned so far. We learned these arithmetic expressions, and last week we learned that these three language constructs are enough to to program anything. So that language, lambda calculus, is Turing complete in a sense that when we have an identifier, function expression, and function call, then that's it. We can implement anything that you want. So in this language, because functions are values, now we have not only numbers, but functions as values. A function value, in other words, closure, is a pair of function expression and its environment. And those two language constructs that introduced for function expressions, when we introduce a function expression that constructs a value, closure V, with the parameter name, body expression, and the environment at that time. For function call, we have E1, E2. E1's value, it cannot be number, but closure, which has parameter name, body expression, and the environment, not sigma, but sigma prime. We evaluate E2, get the value of E2, which is V2. Then remember that the parameter's value is V2. Remember that on top of sigma prime. That's the environment when this closure V was constructed. Using that environment, we evaluate the function body. We evaluate the function body, get the value, that's the value of the function call. Nothing should be surprising to you. Today, we are going to talk about recursion. FAE with recursion. FAE with recursion. Open, close, we are defining a function which has, again, only one parameter, whose body is this expression. Using that function, we evaluate this expression, meaning that this function is available here, but not only there, it's also available in the function body. That's the definition of recursion. If you want to compare this with what? Val ID equals expr. Remember this thing? Expr, close, right? How are they different? Val for non-recursive name, meaning that you can use this name here, but not here. Recursion meaning that you can call this function, you can use this name here and in the body as well. That's the definition of recursion. While we are talking about recursion, why do we need if 0? Yeah, if 0 meaning open some condition expression. If the value of this first sub-expression is 0, evaluate the second sub-expression. If it's not 0, then evaluate the third sub-expression. Why do we need if 0 while we are talking about recursion, which is complex enough by itself? Because if we do not have conditional expression, we cannot get out of recursion. Right? Recursion meaning that there's a loop. We do the same thing over and over again, but we need to go out. Otherwise, it's gonna non-termination. right? It's going to be non-termination. So when we have a recursion, we should have a branch expression as well. The first part of today's lecture is about recursion. We are going to implement recursion without using recursion. I'm going to use this phrase, recursion without using recursion, meaning that we are going to implement or talk about recursion in one language, the target language that we are trying to learn, without using recursion, meaning that without using the recursion that we know of, meaning that we are going to explain recursion without using recursive thingies. If it's not yet clear to you, I'm with you. I'm sure that you are not going to get it yet. And I'm going to repeat this phrase multiple times so that you can get better ideas later. Factorial. It's a famous recursive function. Let's define factorial function, which takes one parameter named n. And the body says, hey, if the parameter n is 0, then the result is 1. 0 factorial is 1. Otherwise, multiply n with factorial of n minus 1. Yeah, so far so good, right? N factorial is either 1 or n times n minus 1 factorial. If n is 0, otherwise, right? You're familiar with this one. So this is just, recursion. Here we have 3 occurrences of the same name fact. Fact here, fact there, fact here, right? 3 occurrences. The first occurrence is the definition of this recursive function fact for factorial. The second appearance is recursive call inside the function body. The third one is the use side of fact outside the function definition. Are you with me? Let me repeat this in Korean and move on. 이거 recursive 함수예요. 재규 함수죠. 여기서 팩토리얼을 선언했고 그 안에 얘를 정의하는 데서 불렀고 이게 recursive call이에요. 이거는 정의한 함수를 호출하는 거예요. We are calling this function fact using the argument 10. So far so good. Nothing surprising. Can we replace that using this val notation, remember? Yeah. Val, fact is a function. It takes one parameter and in the body, just the same thing. If the argument is 0, 1, otherwise do this thingy. Does it work? What do you think? Would it work? No way. Then we would not talk about recursive function today and just use val. It is not available because what? This fact name does not exist in the scope when we evaluate this part, right? Yeah. That's the main difference between recursion and non-recursion. Fact is a free identifier here. Are you with me? Okay, ready? Then, you know what? Val does not support recursive definitions, but still, at the point that we call fact, when we defined this thing, then when we call fact here, we do have fact. We do have the value of fact. And when we introducing this name, right? Open val fact equals E1 semicolon E2, right? Fact is available here but not here. Then we can use fact when we evaluate this expression. We can use fact when we evaluate this expression. So let's pass that fact as an argument. What am I talking about? Yeah, is it clear to you? What did I just say? Because this fact or fact x, this time I just renamed it. Fact x is available when we call that. Fact x is not available in here, but fact x is available here, so we can pass it as its argument. Isn't it crazy? Yeah. So during this first part of today's lecture, I'm gonna tell you a crazy story. So if you get it for the first time, from just first reading or listening, you are a genius. Otherwise, don't worry. I'm pretty sure you'd better want to listen to the story one more time. If it's an offline lecture, I would repeat what I would say multiple times. But because it's an online lecture, and because I already told you that I'm squeezing the material of 2 lectures to 1, I'm gonna go fast. I may not repeat the important concept multiple times as I would do that in offline lecture. So you'd better pay attention to what I'm saying and listen well. One more time. This facx is that facx. I mean, previously we called them fact for factorial, but it takes only one parameter. And now we said that because we know what fact is at this point, we are going to pass it as its argument. So this function needs 2 arguments. So we changed the name to facx, which takes 2 arguments. One for itself. The second one is the usual number argument. So in the definition of the function, the recursive function, what do we have? It has 2 parameters. The function itself and the argument. And the body should be as usual, meaning that if the second argument is 0, it's 1. Otherwise, n times recursive call with n-1, but this time, this recursive call is not facx again, right? Because facx is not available in the function body, but facy is available. So we can call this second argument, and then we also need to pass that as a, well, as this, it's not the second argument, first argument, as the function. Okay? Do you see it? One more time. Because this factorial function, it's not possible for us to call the function in the function body because it's not yet available. It does not exist when we evaluate this expression. So we take it as a parameter. Hey, while we are constructing this closure V, we do not have the value of it. But when you call this, you should have 1. I know that. So when you call facx, just pass itself as its first argument. Then when I need to call the function itself as recursively like that, I'm gonna call that passed argument, the passed function, and then pass it again as the first argument when I call it recursively. Sounds crazy, but yeah, it works. So let's wrap this to get fact back because it looks a bit weird. How can you make it less weird? Oh, look at that. We have this val fact is a function which takes only one number. That's all you need to know. Let's hide this dirty secret. And all you know is that fact is a function that takes one number. Okay, then we can call it with one number argument. That's good. Then what's the body? What's the function body? That's what the usual thing that we had before, facx, which takes 2 parameters. And when we call it, we need to pass it. Are you with me? Yeah? So far, so good? Then what can we do with this crazy trick? What's next? But does it make sense? Because the language that we are using has only one single argument functions, right? Only single argument functions. But how can you make these 2 parameter thingy like that? Yeah, I kind of lied to you, but don't worry, we can simulate this by using functions with single arguments. Meaning that, let's think about this. This f function, it takes 3 parameters, x, y, and z. And then it does some computation. But we can simulate this by using multiple single argument functions. Meaning that, this function says I need 3 arguments, But we can simulate it by saying that give me the first parameter, the second parameter, and then the third parameter. Then we can do the computation. So they are technically different, but yeah, they behave similarly. So we can just use this. How are they different? For this case, we can call function when we have all three arguments. But for this one, we can call this function even with one argument or two or three. Do you see that? When we call this function with one argument, it's going to return a function that expects two numbers. If we call this function with two arguments, then it's going to return a function that expects one more number. If we call that with three arguments, that's just the same. See? Yeah, here, that's a good trick. What's next? Yeah, so then we'd like to rewrite these multiple argument functions to take only one argument by using this trick. How? Yeah, like this. Instead of these pairs, we can just make it nested function expressions, saying that, hey, fegx, it's a function, yeah, as you know, but this time, instead of two parameters, it takes one parameter at a time. One parameter at a time. So, feg_y first, and then take one more parameter and do the usual thing. And this time, because it takes only one argument at a time, feg_y takes one argument first, and then it returns another function expecting a number. When you call this one, previously we called fegx with two arguments, but this time we call fegx with one argument, which returns another function that expects a number, then pass a number. Is it clear now? Do you see that? Now it looks slightly better because unlike previous version, which it takes two parameters and call functions with two arguments that are not allowed by our language, now it can take one parameter at a time and call a function with one argument at a time. Yeah, way more reasonable. But still, wow, there are so many function expressions here, right? There, one more. Too many. We'd like to simplify that so that it looks slightly closer to the original version. What can we do that? Actually, there's a trick called eta reduction. You do not need to remember this name, or you do not need to remember this technique just to try to understand what I'm saying. Just listen to my story. It's a story that's crazy. Look at that. When we have a function expression which has a parameter and use that parameter at the end, but in the middle n is not being used, okay? Then we can get rid of those and simplify that. That's called eta reduction. In general, eta reduction, it's a simplification from this one to that. When we have a function expression whose parameter is used at the end only, and n is not free in expert, and n is not being used freely here, then we can get rid of that and simplify this. Meaning that here we have this function expression. Yeah, n is a parameter. N is being used here, but this n is different from this one, right? This one is binding occurrence, and these three occurrences are bound to here, not there, right? You should be able to see that. So we can get rid of it to this. Oh yeah, much simpler, much better. Then what? See, after that simplification, this one looks almost like the previous one. The original factorial, which takes a number and the usual thing, right? If n is 0, then 1. Otherwise, this recursive call with this crazy name. I hate this name. Yeah? Without this name, it looks almost the same as before. Then let's remove that. Let's rename it by using some better name. More like original, introduce a local binding for that crazy name. So I'd like to replace this with what? Fake, of course, like this. See, now this one is really exactly like the original factorial. It takes a number. If that number is a 0, it's 1. Otherwise, recursive call of n times recursive call of fake with n minus 1. Wow, how can it happen? Because this fake is that. We introduced this name for fake y. Isn't it beautiful? Yes, too good to be true. Oh, sorry. There is a mistake here. What? Because this is an infinite loop. We used to evaluate fake y. We used to evaluate that part only when n is non-zero. But this time, we evaluate this all the time. What's wrong with that? Listen well, this is really important. You should be able to explain why there's an infinite loop. I told you that until now, it was a story. That's a crazy story that we can simulate recursion without using recursion. But you should be able to repeat what I'm gonna say, meaning you should be able to explain why there's an infinite loop. Okay, what is that? Let's look at that. What is this expression? It's an identifier introduction from here to there, and we're gonna use it. Yeah, we're gonna use it. What is fag? Fag is the value of this expression. Okay, what is the value? What is that expression? That's another fag x, whose value is that, and using it. Okay, so what is a fag x? Fag x is, function expression. Remember, evaluation of the function expression does not even need to look at the function body. Remember that? What's the value of that? It's closure v. Fag x, the value of fag x. The value of fag x is closure v. Oh yeah, closure v, whose parameter name is fag y, whose body is from where to where, whatever, that body, the whole thing, and then environment is empty. Oh, isn't it cool? Okay, that's it. And using the value, what do? We are gonna evaluate fag x. Okay, what is fag x? Disclosure v. Okay, what do? We are gonna pass this fag x to this itself. Okay, so we are gonna pass fag x to its body here. Fag y, it's a parameter. What's gonna be its value? Fag x, that closure v. Using that, what are we gonna do? This is the body expression. Okay, again, it's a function expression. So cool. Oh, wait, before that, I'm sorry, there's a fal. Okay, fag. What is it? It's a function call with fag y and fag y. What's fag y again? Oh, you know what? That's this value, closure v. Okay, and what's the argument value? The same closure v. What's the body? The same body. Okay. We are going to evaluate the same body with the same argument. Do you see the cycle? Yeah, there's a cycle. That's why we call that an infinite loop. We don't want it because you do that thingy. 뺑뺑이 돌죠? Yeah, it's an infinite loop. It does not terminate. We do not want to evaluate this all the time. We used to evaluate that only when n is non-zero. Remember, I told you that we need if 0 to get out of the recursion. So, we'd like to delay the evaluation of that. We'd like to evaluate this only when we need to. How? Oh, yeah. In the body, we had to evaluate this one all the time. Because of that, then let's delay that evaluation by wrapping it. You already saw multiple times that when we have a function expression, we do not need to even look at the body. We just need to make a closure v and done. So we do not need to evaluate this part right there. Just pass it, just wrap it as fag. And when the argument is 0, we don't need to evaluate it. But when argument is non-zero, then we can evaluate that thingy. Right? That's how we break the cycle. Now, what about Fibonacci, summation, some other recursive functions? So we'd like to simulate the same crazy trick with all the other recursive functions by having this mkreg function. It's a library function. Mkreg is yet another function expression, right? It takes a parameter and does the usual thingy to make the argument recursive. And then when we define this fact, this mkreg is recursive function maker, and then the argument is going to be some function expression that exactly like original factorial function, then it's going to make it recursive. Wow, that's not magic. And you can do the same thing for Fibonacci by passing this Fibonacci function to mkreg. You can pass summation to mkreg like that. How's that? Isn't it crazy? I know that those things are not really obvious. I warned you in the beginning. So if you don't understand some part, take a break and listen to that part multiple times.